So what do diffusion models do? Diffusion models are trying to learn what noise is added to an image. So during the training process, what we do is we take a extremely noisy image, take an extremely noisy image, and how do we get to this noisy image? Well, we take a real image, and we keep on adding noise to it, keep on adding noise to it, and we're able to skip the amount of noise steps that we do through the shortcut equation. And so we have a shortcut equation that we're able to use that's able to go from time step 0 all the way to time step 50, time step 100 and get to that noisy image. And so we have a real image, we add layers of noise to it to get to a noisy image at a certain time step. And so let's say we have 64 batches of, let's say we have a batch size of 64 real images. Each one of those real images, we're going to sample a random sample time step. Time step, again, chosen is a hyperparameter chosen by the designer. 1 to 1,000, we're going to randomly sample. And that's going to be our time step. And then our inputs to the model are going to be the real image or the noisy image xt, and then the time step t, going to have 64 of those, right? If that's our batch size. So this could be time step 1, time step 2, time step 1,000, randomly sampling from these 1 to 1,000. And then the gradient update is going to be after that one batch. And then we have an epoch is one pass over the entire data set. And then we have the size of the data set over the batch size, and that's going to be the number of gradient updates that we get per epoch. We can have as many epochs as we want as a hyperparameter we can set. And so diffusion models, what are they trying to learn? They're trying to learn, okay, this is xt, which is the noisy image at time step t. This is the amount of noise that was added to this from the original clean image. So it's trying to predict what's the noise that is added from this noisy image at a certain time step. So it's able to learn at many different time steps the noise that is added. And then during the generation phase, what we do is we take a noisy image and we give it, okay, at time step 1,000 or at time step 500 or at a certain t. And what it's going to do is it's going to say, okay, now we're going to denoise this step one step at a time. So it's going to predict what's the noise in this image. It's going to go back, remove that noise to x0, remove that noise back to x0. Then we're going to go back to x99. X99. And why? Because this is not perfect. This is not perfect. This noise that we predicted is not actually perfect. And so because it's not actually perfect, we can't just immediately go back to x0, our estimated original image. We have to say, okay, we estimated some part of this noise, but it's not perfect. And so that's why we go back to x99 and repeat this entire process t number of times to then get back to the original estimated original image. And that's our new generated image. So overall diffusion models, we try to predict what noise was added to an image. And then during generation process, we denoise it, predict what amount of noise is added, and then go back to the previous time step and then keep on doing that t number of times until we generate a new image. So that is diffusion. Take clean image, clean it slightly noisy, very noisy, almost all noise, pure Gaussian noise. And so the network predicts the amount of noise that is added, and we have this shortcut formula that we're able to use. And why are we able to use this shortcut formula? Is because the sum of normal random variables is itself a normal random variable. So we're able to use a shortcut instead of adding noise at every single time, so able to jump to any single noise level in a one shot. Right? Alpha contains how much of the original image from the previous time step you actually want to preserve. We have noise schedules. Noise schedules referring because each time step we want to preserve a certain part of the original previous image. So linear versus cosine. Cosine, what we do, cosine noise schedule, what we do is we slow down earlier, right? So we still keep a lot of the major structures of the image early, and then we add significant amount of noise later on. Compared to linear, what we do when we have a linear noise schedule is we erase a lot of the important structures of the images early on, so a lot of the preservation doesn't happen. Compared to cosine, which we're slowly in the beginning, we're slowly adding noise. We're not removing all of the irrelevant features, slowly adding noise, and then increasing the amount of noise that we do add towards the middle. So that's going to preserve some important features such as the patterns, the shapes, the designs of the image early on. Now, stable diffusion. What does stable diffusion do? So regular diffusion, unconditional diffusion generation is we take just a random noise sample, and then we generate an image. We generate an image. But this is not all that we need, right? We need to be able to generate images of what? Of what? We don't want to just generate a random image. We want to generate an image of depending on the user prompt, depending on what the user actually wants. So that's why we take a prompt and then we feed that prompt through a clip encoder. And so we encode that, and then that's our embedding. So we take the text prompt, feed it to the clip text encoder, get our text embedding, and then we're going to use cross attention. We're going to use cross attention so that when it does do the denoising steps, it's able to see, okay, it's conditioned on we also want to get back to our original image or our image, which is going to be this version of an image based upon what the clip text encoder has provided us. So if it's an image of a dog, it's going to condition on the dog, and it's going to try to say, okay, it's going to try to predict what amount of noise is added to the image of a dog. So it's going to that's the baseline it's trying to get to. That's the baseline it's trying to get to, is the image of a dog. How much noise is added to the image of a dog, and then or to the image of a cat, to the image of whatever prompt that you specified in the beginning, and it's going to remove that denoise that iteratively at t number of times. And now the second thing is we also use a latent. We also use a pre-trained VAE. Okay, so we have this high dimensional image that we then have this encoder and reduce it to a latent space. We decode it from the latent space back to the original image. So the concept here is we're trying to preserve as much information as we can in these fewer dimensions. So it is a dimensional reduction technique that we're trying to do. So we use VAE, and we actually do denoising on the VAE or on the latent space. So we don't actually denoise the original image. We don't denoise the entire, if it's 512 by 512. We don't denoise that. We denoise the much smaller latent space, latent image. And then do cross attention on that, condition on that, clean latent. After we get to the clean latent, then we do the VAE decoder, and then we're able to get to the final image. So we have text encoder, UNet. UNet is the model that actually predicts the noise. Now classifier-free guidance. So we talked about text conditioning alone. So it just loosely follows the prompt. So this is a way for you to specifically signal how much weight you want to give to directionally prompt it in the way that your prompt suggested. So your prompt may be a dog or a cat, but one of the issues of traditional stable diffusion is that it's not able to accurately and coherently abide to that prompt. So you want to make sure that you want to nudge it in the direction of the prompt as much as you can. And so if we have a greater weight to this, it's going to overemphasize the prompt. If we have too small of a weight, it's almost going to ignore the prompt. So this W weight controls how much attention we want to give to the prompt, and gives more emphasis and importance when it's conditioning on the prompt and using that. So now we also have control net, DDIM, control net, and these other key variants. This one adds a prior network in the sense that in stable diffusion, we just use a text embedding. Now what we're going to do is, instead of that text embedding, we're going to see what the image embedding is of clip from that text embedding. So it's another network that predicts the clip image embedding, and use the clip image embedding in our diffusion instead of the regular text embedding. DDIM versus DDPM. What does DDPM do? DDPM, you go incrementally through each of the steps. So when you're doing the generation phase, if you're starting at 1,000, you go to 999, you go to incrementally into 1,000 time steps until you get to the generated image. And why do you do this? Is because you go from X 1,000, you go to the estimated original image, and then you go back to X99. But here you can actually skip steps, so you can go directly from X1000 to you can go to X950. And why are you able to do this? Why are you able to do this? Is because of the shortcut equation that we have. Able to directly skip steps. Able to directly skip steps without retraining. Now let's talk about GAN. So GAN, we have a generator discriminator. The goal of the generator is to fool the discriminator into thinking whatever images it creates is actually real. So the goal of the discriminator, or the goal of the generator, is to get a probability that it's real, try to maximize this probability that the image it generates is real from the discriminator. And discriminator is going to try to correctly classify, is going to get a batch of real images, going to get a batch of fake images from the generator, wants to correctly classify if it's a fake image, wants to give a low realness probability score if it's a probability, right? If we contrast this with other variants of GANs, it's not a probability, but it's actually a realness score. But here it's actually a probability in traditional GANs. We want probability of real to be as high as possible, as high as possible. Right? That's the goal for the generator. It's going to produce an image. We want the discriminator to think that this image is real. And discriminator is going to say, okay, we want to accurately classify these images. Probability of real will be high for these images. Probability of real going to be low for these other images. And now this is the minimax objective. So we have two opposing adversary connections here. So G is going to, generator is going to want to minimize this objective function. The discriminator is going to try to maximize this objective function. Right? Maximize is going to real data high scores, fake data low scores. Right? D of X is the probability that the image is real, that the discriminator gives. G of Z is Z is a latent space, right? Latent space randomly sampled, and then G is generator. We produce a fake image. So DG of Z is what the discriminator's probability score to that generated image from the generator. And equilibrium, theoretical equilibrium, is when we get to a perfect state. The generator is going to produce an image, create an image, and the discriminator will give a probability of 0.5 because it can't determine whether it's fake or if it's real. It can't determine if it's fake or real. So that's the ideal Nash equilibrium. D can no longer tell real from fake. So that's as the discriminator gets better and better, the generator gets better and better at producing what looks like to be real images. Training can be unstable, but we have vanishing gradient, we have mode collapse, where the generator finds one extremely good patterns of images that it reliably fools D, and so it only then generates those patterns and doesn't actually explore the entire space and the true diversity of real images that it can generate. So that's mode collapse. Mode collapse, right? The generator is just going to create and produce these one set of patterns of images that fool the discriminator. We have JS divergence. Difference again. These are JS divergence, KL, and then we also have W distance, which again measure the difference between real and fake distributions. And now we'll compare KL divergence, JS, and then W distance. So KL divergence, asymmetric, go up to infinity. If fake distribution misses real data support. JS divergence takes KL divergence, but now it's actually symmetric, and we actually bound the scores. And now W, Earth mover distance, it measures the work that needs to be done to move one distribution onto the other. And it stays smooth and informative even when the other distributions are far apart. And so we use, in WGAN, we use this other loss function, right, with the critic, and this critic is going to give an unbounded realness score instead of a probability. It's going to give this realness score. So it's going to be unbounded. Key variance, you have conditional GAN, cycle GAN, style GAN. Style GAN, we have a mapping network, untangles noise into a style space, and you inject that at different layers. And then now we have normalizing flow. So normalizing flow, every single transformation is going to be invertible. Every single transformation is going to be invertible. So what it's going to do, it's going to try an invertible mapping between this complex data distribution to something a simple Gaussian normal distribution, Gaussian distribution. Right, mean zero variance one. Mean zero variance one. So it's going to try and learn this invertible differentiable mapping. So what we do is we take these real images, and we're going to try to map them into the latent space and the dimensionality of the latent space and the real images will be the same. So we make sure all information is preserved and we make sure that every single transformation is invertible such that if we were to go back from the latent space, there is only a one-to-one relationship. So a single point in latent space corresponds to only one particular real image. And it's invertible. And these transformations are invertible. And now during training, what happens during training is we have these real images. During training, we have this contrastive element where we have these real images and we also have fake images in energy-based models. For flow models, typically you just have real images and we try to map them to latent space. And then for the generation, we take sample a random latent space, point in latent space, and we're able to generate a real image. And we just reverse back because these transformations are invertible, we just reverse the layers. We reverse the transformations. So here is what are we saying here is that the probability that this image occurs or exists from the learned model data distribution is the probability of this point in latent space times the amount that the density was compressed or changed. So that's the determinant of the Jacobian. And we take the log of that. We have the change of variables as well. That's the change of variables formula, and then we take the log. It's easier to minimize coupling layers. These are the ingredient because we want a Jacobian that's easy to calculate. We want invertibility. Easy Jacobian to calculate, and we want invertibility. So what do we do with these coupling layers? Is we have these inputs, XA and XB, from our original image matrix. And then we have XA is exactly the same. And then XB, we apply this transformation. Okay? And then SXA is a neural network, output of a neural network. TXA is also output of a neural network. But you can see XA remains unchanged. And this allows this layer to be invertible. So allows this layer to be invertible, also makes the Jacobian easy to calculate. And now what Glow's improvement did is what we do here is we take, okay, now XA didn't change in the next coupling layer. We're going to now change XB and then keep XA, we're going to keep XA the same. Now XB is going to be the same, and then we're going to change XA. So we do this over and over again, change one variable, keep one variable the same, then flip those, change the other variable, keep that the same. But now Glow's improvement, and we're going to do this learned mixing. We're going to do this learned mixing where even the permutation of how much we want to change, right, the order is going to be learned. And so that's what we do, a one-by-one invertible convolution. Energy-based, let's go over energy-based, is we want to have low energy scores for real data, and we want to have high energy scores for fake generated data. And we do this through contrastive learning, where we take these fake images, we generate these fake images. How do we generate these fake images? Take random noise, and each update, we try to get to a state of lower energy through this gradient update rule. once we try to make an image that has extremely low energy, so this is similar to the adversarial connection. We want to, during the process of creating a fake image, we want to create an image with a very extremely low energy. And after we've created an image with an extremely low energy, then we want to compare that against a real image. So we want energy score of a real image. So this is the loss energy score of real images minus the energy score of fake images. And we want the energy score of real images. We want to push their energies down. We want to decrease their energies of real images. Right. So we want to increase the energy scores of these model generator, these corrupted and negative samples. Right. And then how do we sample? Apply this gradient steps. Take the gradient of the energy function and and then add some random noise. So it also explores, instead of just taking the optimal path every time, also explores some randomness to it. And then we also have this replay buffer instead of starting from scratch, but every time we actually keep track of the previous fake images we've generated, and then we start from there. So we get a better fake image to learn from. And then we update the weights after each batch. So we sample real data from the data set, generate these negative samples using the gradient update subrule in Javian dynamics, compute the energy of both batches. And again, when we're doing generating, we want it to be real looking. So low energy, compute the contrastive loss of the batches. So the average energy score of real images, average energy score of fake images. And then we update the network weights through gradient descent. And then we store those negative samples, replay buffer again. And again, exact normalization is intractable in high dimensions. If you want exactness and you want to measure the likelihood exactly of this image under the model's learned data distribution, then you use normalizing flow. But here it's intractable. Here it's intractable. That's why I use contrastive learning technique. Music transformer is just next token prediction. So everything you know about transformers decoder, same, except what do we call a token? Here is a musical event. And a note is a series of tokens. So a note, a duration, everything is a series of tokens. A token here is just a musical event, and this is just next token prediction, the same thing you do in typical transformers, except this is now for music. MuseGAN, we know MuseGAN. We have these 4 separate latents. Generator builds the whole multi-track block at once, and we have these critic. There's no batch norm in the critic. And that's it.